So I congratulate all you for choosing this AIMS Institute for your career growth, and I wish you once again a happy new year to all. So in this real analysis lectures, I am going to start with bounded sets, and then Supremum and Infimum, and then Archimedean property for today's class. You may expect at least one question from this topic. Okay, so I will define concept first, and then later I will do problems on the concepts what we are going to discuss. So my motto is, if we know the concept well, then we can answer any kind of problem. Am I right? Hello?
సార్ మీరు అన్మ్యూట్ చేసుకొని మాట్లాడొచ్చు సార్, ఎవరైనా సార్.
Hello, in between you can say I am audible, then you can say yes, it is audible. In between I may ask, yes, is my screen visible to you? Then you can speak out, yes, it is visible. Or do you have, yes, any thoughts in between? You can raise your hand and say, or you can stop me at any time and you can raise a question. So this is a different structure. If it is an online, offline class, then we can see the students' faces. Yes or no? So with this brief introduction, so I am going to define what is a bounded set. First we define what is an unbounded set, bounded above set, bounded below set, and so on. So first I am defining bounded set. So you please tell me, is my handwriting visible to you or not?
Yes, sir.
Hello? Yes.
Sir.
Okay. So now I am defining bounded above set. So roughly speaking, bounded above set means all the elements of a set are left of some real number. So this is a small m. So this is I am explaining or defining roughly or loosely speaking, a set is said to be bounded above if all the terms of the set are left of some real number. So this is a rough definition I am writing here. All the elements of a set are left of some real number. So this is what a bounded above set, and such this m are called an upper bound of the set. So precisely now I am defining what is a bounded set. So let A be a non-empty subset of R. Non-empty subset of R. Right? We say that A is one second. We say that A is bounded above if there exists m belongs to real number set such that x is less than or equal to m. This is true for all x belongs to R. For all x belongs to the set A. Then we say that the set is bounded above. So here, this such m's are called an upper bound. So here, this m is called an upper bound. M is called an upper bound. Is this clear? So now look at the rough definition and the precise definition. If all the elements of a set A are left of some real number, then we say that the set is bounded above, and such m's are called an upper bound of a set. So we write here upper bound as ub. So ub is m here. Okay. Similarly, we define a bounded below set. So we define what is a bounded below set. So bounded below set. Below set. The definition is almost similar to the previous one. So roughly speaking, all the terms of the set or all the elements of the set this time are right of some real number. So these are dot dot dots. These are elements of a set A. If all the elements of A are right of some number, some real number, then we say that the set A is bounded below. So precisely we write the definition of a bounded below set. Let A is non-empty, A is not equal to non-empty, and which is subset of a real number set. We say that A is bounded below. So I'm writing BDD for bounded below if there exists some real number belongs to R such that, now look at this one, all the terms of the set are right of some real number. How do we write that? So m is less than or equals to x for all x belongs to A. Then we say that the set A is a bounded below set. And here the small m is called such an m, or each such real number is called a lower bound of m. So here each such real numbers m are called lower bounds. Lower bound. Lower bound of A. Hello? Are you following?
Yes,
Yes,
sir.
sir.
Okay, done. Now we define what is a bounded set. Now I am going to define a bounded set. Now you are well aware of this one. So bounded set. When can we say that a set is bounded? If it is both bounded above and bounded below. Again, let A is non-empty and subset of R. And we say that A is bounded. So I'm writing BDD for bounded if it is both bounded above and bounded below. Then the set is known as a bounded set. So this is one definition. This is the combination of the above two definitions, right? So I will define a similar definition for a bounded set as follows. Okay, you call this as definition 1 for bounded set. So why I am defining multiple definition for the same set? Because it is easy to understand the concept. Okay, so for that reason, I am defining one more definition for a bounded set. Correct? A non-empty set A, which is subset of R, is called, or is said to be, is called a bounded set. Bounded set. If this time we are I am writing, there exist two real numbers, small m and capital M belongs to R, such that, so this is bounded below, definition for bounded below, and this is the definition for bounded above. And this is true for all x belongs to A, then we say that the set is bounded. Or loosely speaking, if all the terms of the set or all the elements of a set are lies between two real numbers, then we say that the set is bounded set. Or I will define one more definition which is almost related to this one, right? We say that a non-empty subset A of R is a bounded set. Is a bounded set if there exists a closed interval, all we know what is a closed interval, say A comma B, such that all the elements of A are belongs to this interval. So that is x belongs to this closed interval A comma B, and for all x belongs to A. Then we say that the set is bounded, and one can prove that definition 2 implies definition 3. In definition 2, if I take small m as small a and capital M as B, then definition 2 is same as definition 3. Okay. Now you tell me, are the definitions clear? Hello? Definitions
Yes, sir.
of bounded. Yes, sir. Bounded. Oh, fine. Now I'll write one simple example. So if I take this one, so I'm taking very simple example. Say 1, 2, 3, up to 10. Is this set bounded? Yes,
Sir.
it is a bounded set, because if I take my small m1 as 1 and capital M as 10, then all the elements of A are lies between 1 and 10. So this is true for all x belongs to A. So therefore, A is bounded. Okay. So this is a finite set, right? So the next example is every finite subset of a real number set is bounded. So example number 2 is every, I'm writing in a statement, every finite, this is very important, finite subset of R is bounded. This is bounded. I'll prove it in a line. You take any finite subset of R, then it must be a bounded set. So proof is trivial. So this is the trivial statement. The proof is this one. Now A, I'm taking A as a finite set, and elements of A are say A1, A2, A3, up to say AN. So this is a finite set. So therefore cardinality of A is n. This is finite, right? By law of trichotomy or well ordering principle, we can arrange the elements of A in an increasing order, right? So without loss of generality, without loss of generality, I am assuming A1 is less than or equal to A2 is less than or equal to A3, or we can compare and we can make an increasing sequence of elements of A. Now you see, if you take small m equals to A1 and capital M equals to AN, then all the terms of the set A are always lies between the small m and capital M for all x belongs to A. So therefore, we say that A is bounded. So this is a trivial example. Now you can check any finite set or subset of R which is always a bounded subset. All right. And next we see unbounded set. When can we say the set is unbounded? Right? Unbounded set. So we say that a set is unbounded if it is not bounded. Right? So I am writing definition for an unbounded set. Right? A non-empty subset. A non-empty subset A of can write small a or capital A itself. A non-empty subset A of R is unbounded. It is unbounded if A is not bounded. If it is not bounded, then we say that it is. Now, when can we say that A is not bounded? Means if A is either not bounded above, or we say uh, A is not bounded below, right? In this case, we say that the set is unbounded. So this is we can call this definition as a rough definition, right? Precisely, I am defining what is an unbounded set as follows. A is non-empty subset of R, right? And then we say A is unbounded above. I am defining what is an unbounded above set. Unbounded above if for every m belongs to R, you can take any real number. There exists x belongs to A such that what happens? Can anyone guess? Such that small m is less than x, right? You check any m belongs to R. Now I can find an element A in x in A such that x is more than m, right? So I will explain this through a simple example as follows. Example. So this one. So this is a very simple example known to us. So the set of natural numbers. You take this one, say 1, 2, 3, and so on. So this, you can take any real number. I can find a natural number, which is precisely the Archimedean property. Later we prove it, Archimedean property. So I am stating in advance. So with the help of Archimedean property, we can claim that you give me any real number, I can find a natural number which is greater than the given real number. So therefore, this is unbounded above. This is unbounded above set. Unbounded. Right. Similarly, we define unbounded below. If it is not bounded below, then we call it as an unbounded below. If it is not bounded above, then we say that it is unbounded above. So one more definition: unbounded below set. unbounded below. A set which is not bounded below. So this is precisely, we can say, not bounded below, right? Not bounded below means which is unbounded below, right? Or we write, we define precisely a non-empty subset A of R is unbounded below. Unbounded below if you take any real number, then I can find an element in A that exists x belongs to A such that what happens, x is always less than m. If this is, then we say that the set is unbounded below. Right? Hello? Are you following? Yes, please.
Yes, sir.
Yes, please.
Okay, fine. So I'll write a small remark here. So if m is an upper bound, if m is an upper bound, then you take any number more than m, means then m plus 1, m plus 2, plus so on are also upper bounds. Are also upper bounds. Upper bounds of A. This is trivial because what if m is an upper bound, then what happens? X is always less than or equal to m. This is true for all x belongs to A, right? Now you take x is less than or equal to m. It also holds for m plus 1, also holds for m plus 2, and so on. So therefore, if m is an upper bound, then m plus 1, m plus 2 more than m is also an upper bound. And similarly, if small m is a lower bound, then any number less than m is also a lower bound. Then we write m minus 1, m minus 2, and so on are also lower bounds of set A. If small m is a lower bound, means what? M is less than or equal to x for all x belongs to A, right? Now you take any number less than m. So this is m minus 1. Also same inequality holds. If I write m minus 2, then also the same inequality holds. So therefore, if m is an upper lower bound, then any number less than m is also an upper bound. So we say that if m is upper bound, the upper bound is not unique, and similarly lower bound is also not unique. Hello? So this is one observation from the sets. And the next one
Okay,
is,
sir.
okay, upper bound and the lower bound may not be an element of the set. May not be an element of a set. Right? If the upper bound exists, then the upper bound may not be an element of the set. Similarly, if the lower bound is there, then the lower bound may not be an element of the set A. Right? May not be, may or may not be an element of A. Okay. I'll give you some simple examples where the lower bound belongs to the set, lower bound may not belongs to the set, upper bound belongs to the set, and upper bound may not belongs to the set. So I'm writing in examples. Now look at a simple example. So if I take A equals to this set of all real numbers, lies between x and 2, right? So clearly, so you can raise it if you have any doubts. Clearly, upper bound is 2, right? Because all the elements of A are less than 2. So therefore 2 is an upper bound. But 2 does not belongs to A. But 2 does not belongs to A. So here upper bound is 2, but this is not in the set A. So this is example 1. So example 2 I am defining. If A is this set, so x belongs to R such that 0 is less than x is less than R equals to 2. So this time I am included 2 in the set. So upper bound is 2 and which is belongs to the set A. Right? Now similarly I will define example 3 as follows. I can take the example 1 for the next example 3 and example 1 are same, or I can take a different one. Say take 1 is less than x is say less than 10. Clearly, what is the lower bound? Can anyone guess and tell me what is the lower bound of this set?
1.
It is 1,
1.
but 1 does not belongs to A.
Sir, in first example,
Hello?
0 is also lower bound, does not belongs to set, sir.
Exactly. Exactly. I said the same one. Example 1 I can take as example 3. Huh? So now example 4 is I am taking A as, now this time I will include 1 or I will write one more example. So 0 is less than x is less than say 8. Okay. So here lower bound is 0 belongs to the set A. Upper bound is also 8 which also belongs to A. So from this example we can conclude that lower bound and upper bound may or may not be the elements of A. Is this clear? Hello?
Sir,
Yes,
clear.
sir.
Okay.
Yes, sir.
Okay. Fine. Fine. So next I'll give you some other examples which are trivial, known to you. N is not bounded, Q is not bounded, R is also not bounded. All right. But N is, if I take Z is also not bounded, set of integers. But this N is bounded below because 1 is the least element of N. This is bounded below. And the remaining sets are Q, R, and Z are not bounded sets. Okay. I will go for one more example of bounded sets. Quickly, I will finish this. So if I write this interval, closed interval A comma B is bounded, left open, right closed is bounded, left closed, right open is bounded, and open interval A comma B where A is less than B. All these sets are bounded sets. These are bounded sets, right? Okay. So one more example. So if I write set of reciprocals of natural numbers, n belongs to n. Is this set bounded? Hello? So
Yes, sir.
clearly, what are the elements of this set? 1, half, 1/3,
Bounded, sir.
1/4, and so on. So this is precisely 0 is less than 1 by n is less than or equals to 1 for all n belongs to the set of natural numbers. All right? So clearly 0 is the lower bound, 1 is the upper bound. So therefore this is a bounded set. This is bounded set. Okay. So this is a bounded set. One more example. So this is, now you tell me this one. So this example I'm considering. So if I write this one, this set, I'm calling this set as A. So x plus 1 by x such that x is positive. So this is strictly positive because it is not defined at x equal to 0. Now, can anyone guess and tell me, is this set bounded? If it is bounded, then what are the bounds for this set? I will pause for 1 minute and you can discuss. Is this set bounded or not? X plus 1 by x, provided x is positive. So, any answer, any guesses?
Not bounded, sir.
Not bounded. Fine. Is it bounded above, unbounded above, or unbounded below? If it is not bounded, means either it is unbounded above or unbounded below or both.
Bounded below, sir.
Unbounded above. Unbounded
Bounded
above.
below, but not bounded above.
Bounded above.
Yes, right. So
Okay.
the simplest trick is to show that this set is bounded. Below is, we use this inequality. Arithmetic mean is always greater than or equal to geometric mean. So now I am writing arithmetic mean of x and 1 by x, which is half, and which is always greater than or equal to x times 1 by x, and this is 1. So therefore x plus 1 by x is always greater than or equal to 2. This is true for all x till x is positive. So therefore this 1 is a lower bound. So this one is a lower bound and it has no upper bound. So therefore we say that this set is bounded below but not bounded above. So I am writing here A is bounded below but not bounded above. But not bounded above. Okay. And one more example. This is, I think it is trivial, but we have to discuss this one. So I'm calling my set as yes this time. So x is a real number such that x cube is less than 8, or I can write equal 8 also. Nothing about equality here. Now can you guess, is this set bounded below or bounded above, or unbounded below or unbounded above? Yes, please.
Bounded above, sir.
And what about bounded below? Is it bounded below? You are right. The set is bounded above, but not bounded below.
Bounded below.
But not bounded below. What I'm saying is, this is not bounded below. So now you look at and how do we show this is not bounded below? Because I am drawing a graph of the line, the function y equal to x cube. X cube is an odd function, so it's symmetric about y-axis, right? And I'm drawing the line x equal to 2. So this is the line somewhere x equal to 2. So these two are intersecting it. So whatever the real number you take, x cube cannot exceeds 8 means, and if x is going to be negative this direction, then the graph of the function is goes to be minus infinity, which is always less than 8. So therefore, so this is bounded above, but not bounded below. Later we define what is the infimum and supremum of this kind of sets. Okay, so for that reason I am discussing the same question here. So one more example, then I'll move to next concept. So suppose if you take this one, say S equal to this set, x belongs to Q such that x square is less than 4. Is this set bounded? X is a rational number this time. X is rational and x square is less than 4. Is this set bounded?
Yes, sir.
Yes, it is bounded because we write this x square. We find what are the rational numbers which satisfies this inequality, and the inequality is equivalent to this one. And this we write, or we can factorize this as x plus 2 into x minus 2, which is less than 0. This means x is lies between minus 2 to 2, right? Now what are the rational, whatever the rational number lies between minus 2 and 2, so here minus 2 is a lower bound of that set is, and 2 is an upper bound of that set is, right? Hello,
Yes.
is this
Yes,
explanation
Clear, sir.
okay for you?
Yes, sir.
Yes, sir.
Okay.
Clear.
In
Yes, sir.
fact,
Clear.
any rational number lies between minus 2 and 2 are always bounded by 2. Or in other way, we can write the same inequality as if x square is less than 4, this implies mod x is less than 2, right?
Yes.
So we
Yes.
can write one more definition of a bounded set with the help of modulus also. So I'm writing here. So a set A is bounded. Suppose A is bounded, then there exists m belongs to R plus a positive real number, such that this reminds me to define one more definition of a bounded set, such that modulus of x is less than or equal to some number m, positive number m, and this is true for all x belongs to the set A. Then we say that A is bounded set. So you call this as definition 4 for the bounded set. A is bounded, then there exists, so m is missing here, I'll update it. There exists m a positive real number such that mod x is less than or equal to m for all x belongs to A. Then we say that the set A is bounded. So with the help of this definition, we say that the set is obviously bounded and bounded above by 2. Okay, na? Hello?
Clear, sir.
No, this is the last example.
Yes, sir.
I'm taking
Yes,
this as say 0, 1 union 2, 3, closed interval 2, 3. Now is this set bounded above or bounded below or bounded?
Bounded,
Hello?
sir.
Bounded.
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 Right? This set is bounded because we can write the elements of the set as follows. 0 is less than x is less than 1, so there is an equality, and the union I'm writing informal way, so this is 2 is less than x is less than or equal to 3. So 0, this 0 is the lower bound and this 3 is an upper bound. So then you can check any number between any number from the set S, which are always lies between 0 and 3. Okay, so therefore the set is bounded. So this is bounded set. Okay, now you can think of, suppose A is bounded, B is bounded. Can we say that their union is also bounded? Can we say that their intersection is also bounded?
Yes, sir. Bounded.
Okay, union and intersection of two bounded sets is again a bounded set. You can prove it easily here. So now my favorite example is this one. Is the empty set? This is required for me for the next next concept. Is the empty set bounded?
Yes,
Yes,
sir.
sir. Bounded.
Why?
It is a finite set, sir.
Finite set means it has some elements, right? But empty set has no element. Yes, the answer is yes, it is bounded. Empty set is bounded. Why? Right? Now look at the definition 3 of a bounded set. A set is bounded if there is a closed interval such that all the elements of that set belongs to that closed interval, or you can recollect Every finite set is a bounded set, right? Hello?
Yes.
Every
Yes,
finite
sir.
set is a bounded set, and we
Yes,
know
sir.
that empty set is a subset of uh, any set, right?
Bounded. Yes, sir.
Yes. Empty set is a subset of finite set, and finite set is bounded. Therefore, pi is bounded. Or
Yes.
otherwise, I will explain in another way. Empty set is a subset of any set, right? It could be a subset of any set. So therefore, empty set is a subset of closed interval small m comma m, and this is bounded. So therefore, all the elements of R in this one. Therefore, empty set is bounded. Hello? So
Yes,
this
sir.
is
Yes, sir.
another way
Yes,
of
sir.
arguing the same concept. Okay. So with this, I am stopping, and now I am moving to least upper bound and the greatest lower bound. Okay. So now I am defining least upper bound. Least upper bound. Or we write it as LUB, which is same as Supremum. Supremum. Least upper bound. Later we make a difference between Supremum and the maximum. Okay. Maximum may not be, if maximum exists, then it may be a supremum, and supremum may not be a maximum. But there is a slight difference between them. Later we think of this one. Okay. Now I am defining least upper bound for a set. Let S be a non-empty subset of R. Non-empty, same subset of R. Okay. So I am defining definition A for this supremum. If S is bounded above, S is bounded above, later we remove this bounded above also. Then a number, say U, this number U is called, or is said to be, is called least upper bound. Least upper bound of S if it satisfies two conditions. If it satisfies two conditions. Okay, I'll write what are those two conditions. So first one, U must be an upper bound of S. U must be upper bound of S is an I am writing UB for upper bound of S. And the second one is, if V is any other upper bound, if V is any upper bound of S, UB of S, then what happens, U is always less than or equals to V, right? So this is the least among all the upper bounds, is known as supremum, or the least upper bound of a set. So definition, look at the name, but the least upper bound means least among all the upper bounds
Upper
of
bound.
S, right? So it's known as least upper bound, and we designate this least upper bound as LUB. of S or supremum of S, SUP, supremum of S. Okay. Now similarly, one can write definition of infimum or the greatest lower bound. So I will define this one and later we'll move for examples. Okay. So greatest lower bound. We are calling this as infimum. Infimum, greatest lower bound. Okay. So S is the above set. We say that I'm again using the same letter U. We say that U is a greatest lower bound. Greatest lower bound. Yes, if it satisfies the two conditions. If it satisfies two conditions. We'll go a little bit faster. Two conditions. And can anyone guess what are the two conditions? One must be
U is lower bound.
first one. First one, U is a lower bound of S. Lower bound of S. And second one, if V is any lower bound of B, a lower bound of S, then what happens? Then V
Greater than or equal to V.
V is less than or equals to U. Right? So this is here U is the greatest among all the lower bounds. If V is a lower bound, then V must also less than or equal to U. Right? And this is designated with GLB of S or simply infimum of S. Right? Infimum of S. Okay? If infimum or supremum of a set exists, then it is unique. Okay? If the infimum of a set or supremum of a set exists, then it is unique. So we prove it in a single line. So note that. Supremum of S exists, then it is unique. Then it is unique. Unique means there is only one. Right? Suppose if there are two supremums, suppose not. So you take U1 and U2 be two supremums of S. Supremums of S. If U1 is supremum and U2 is an upper bound, then U1 is always less than or equal to U2. And if U2 is supremum, then U1 is an upper bound. Therefore, U2 is always less than U1. So combine these two. So we have U1 is same as U2. So therefore, if supremum exists, then it is unique. There is no special about supremum. In place of supremum, you can replace by infimum. So if infimum of a set S exists, then it is unique. You can prove it. It's not so difficult one. Right? And one more. Is supremum is always an upper bound? Is supremum is always an upper bound? Hello? Can anyone?
Yes, sir.
Is supremum of a set is an upper bound? Yes, it
Yes,
is.
sir.
Supremum is always an upper bound.
Infimum
Where
is
in the
always lower bound.
Yes, exactly. Supremum of S is always an upper bound, and similarly, infimum of S is always lower bound of S. We can write of S. Okay. Now I will move to some simpler examples, and then later we move for properties of supremum and infimum. First, I am moving to examples. Okay, so you take any finite bounded interval, then we can talk about their infimum and supremum. Right? So this is the example. So I'm taking S equals to closed interval A comma B. Now you tell me what is the supremum of this one. Closed interval, left closed, right open. I can write one more. Left open, right closed, and both open ends. In each set, or for each set, supremum of S is, can anyone guess?
B.
B is the supremum, exactly. And what is the infimum of S?
Small a.
Small. This is obvious. Supremum and infimum of S are clearly A and B. Suppose, so one more example you look at. If A is less than B is less than C, then can you tell me what is the supremum of this set? Supremum of A union B union B union C.
Supremum is
What is
C.
exactly supremum is C. And what is infimum of this one? What is
A.
infimum of this one? It's small. It's obvious. Okay. One more example. So these are quite interesting examples. This one. So example number 2. So I'm taking A as, or A1 as this one. Say 1 by n such that n is belongs to n. Now you tell me what is the supremum and infimum of A1.
Infimum
is
0, supremum 1.
Exactly. Clearly, 0 is less than 1 by n is less than or equal to 1 for all n belongs to n. So therefore, set A1 is precisely left open right closed interval. By the previous example, the supremum is 1 and infimum is 0. So this is precisely, A1 is precisely this interval, 0 to 1 interval. So therefore, supremum of A1 is 1 and infimum of A1 is 0. Okay. So example 3. Example 3 is the following. Suppose if I take A2 as this one, 1 by 2 power n, such that n is a natural number. Can you tell me what is the supremum and infimum of this set?
Supremum 0.
Infimum
Supremum 0,
is
infimum 1 by 2. Supremum
oh.
0.
1 by 2, 1 by 2, 1.
So what are the
supremum
elements
1
of
by 2
this set?
infimum
And
0,
0.
sir.
1 by 2 and 0.
1 second, 1 second. What are the elements of this set? 1 by 2, 2 square, 1 by 2 cube, plus so on, right? Okay. Or we write 0 is less than 1 by 2 power n is less than 1 by 2 for all n belongs to n. Is this clear? Hello?
Sir.
Or
Yes, sir.
A2,
Clear, sir.
yes,
Yes, sir.
please. A2 is same as left open, right closed interval. So this one 1 by 2. So therefore, infimum of A2 is 0 and supremum of A2 is half. Okay. So now look at example 3. Example say 4. This one. So x belongs to R such that x square is less than 10. What is the supremum and infimum of this set? No. So this is easy. So
Minus 10
x
plus 10.
square. No, sir, not plus 10 and minus 10. So this x square is less than 10. So therefore we write it as mod x is less than or equal to or less than root 10. And we know this property. If mod x is less than a, then we write this as minus a is less than x is less than a. So utilizing this, we write this inequality as minus root 10 is less than x is less than plus root 10, or so call this as a3. So a3 is precisely this interval, open interval minus root 10 to plus root 10. Is this clear? So therefore, supremum of a3 is root 10 and infimum of a3 is minus root 10. Agree? Agree with this? Hello?
Clear, sir. Clear.
Sir. Yes,
Yes,
sir.
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 Fine. And this is quite interesting. Please tell me what is the infimum and supremum of this set. So another example. So I'm writing A4. You collect a set of all real numbers such that x square plus x plus 1 is positive. Now you define or you find what is infimum of A4 and supremum of A4.
Does not exist, sir.
Both does not exist, huh?
Both, sir.
Yes, sir. Yes.
Both does not exist. Why?
Because of the quadratic expression has complex roots.
Oh, fine, sir. Infimum is minus infinity in this case, means does not exist. We write does not exist, or plus in minus infinity, and this is plus infinity. I'll tell you why. So this set A4 is equivalent to this one, minus infinity to plus infinity, which is the entire real line, right? Why the set A4 is entire real line? Because whatever the real number you take, x square plus x plus 1 is always positive. This can be ensured by calculating the discriminant of this quadratic expression. So what is the discriminant for this quadratic expression? X square plus x plus 1, which is b square minus 4ac, so which is minus 3 always less than 0. So therefore, this quadratic expression has no real root and its graph always lies above the x-axis. Somewhere here is when x equal to 0, it's a parabola, right? So graph will look like this, right? So therefore, whatever the real number you take, this expression is always positive. So therefore, the set A4 is same as minus infinity to plus infinity, our set of real numbers. So this has no supremum and no infimum, which we write it as minus infinity and plus infinity. So if I reverse the inequality, then what happens? So now I am moving to example 5, or A5 I am writing, so this one. So I am just reversing the inequality. So x belongs to R such that, so this happens, x square plus x plus 1 is less than 0. Right? What is the supremum and infimum of this one? Yes, please. See, now look at the example
It remains the
A4.
same, sir. Again, it remains the same.
Now look at the A4. Whatever the real number you take, that expression is always positive. In A5, it is asking to find those real numbers for which x square plus x plus 1 is negative, which is impossible. So this set is an empty set, right? Clearly, A5 is an empty set. Okay?
Okay, sir.
Is
Okay,
this?
sir.
Okay. So in A4, it is that whatever the real number you take, x square plus x plus 1 is always positive. But in A5, it is asking that find the real numbers where the expression is negative. So there is no x for which the given expression is negative. So which means the set is an empty set. And what is the supremum and infimum of empty set? What is the supremum and infimum of an empty set?
Supremum
Actually,
is minus infinite.
supremum is
Infimum is plus infinite. Supremum
so
is minus infinite. Infimum is plus infinite.
exactly. Why? So infimum of A5 is plus infinity. This is the only instance where supremum is less than an infimum. There is no other, right? This is the only one example where supremum is less than infimum. Later we'll prove that infimum of a set is always less than or equal to supremum of a set. Okay? Or this we can ensure by showing that empty set is a subset of small m comma capital M. So therefore, every m, every small m is an infimum. But what are the m? You can take any real number, right? And capital M is a supremum. And how many such m's are there? Infinitely many, right? Okay, I'm taking one more example of the same kind. This one. So this is my A6. I'm working on A6. Now you tell me what is the infimum and supremum of this set. Then X is positive. Hello? What is the infimum and supremum of this set?
Infimum 0.
Infimum is 0.
Supremum
Infimum
Supremum
1,
is
sir.
2.
Okay,
Supremum
so we
Infimum,
will,
infimum 0, supremum 1, supremum 2.
okay,
Supremum
okay, okay, okay. Now we look at. So again, I am using, previously we have already discussed the same question. This set is bounded below but not unbounded above. So therefore, it has a lower bound, means it has a supremum, the infimum, and it is unbounded above, means it has no supremum. So I will show it. Arithmetic mean is always greater than or equal to geometric mean. Now I am calculating arithmetic mean of x and 1 by x, so which is half, greater than or equal to geometric mean of x and 1 by x, which is just 1. So therefore, x plus 1 by x is always greater than or equal to 2 for all x is positive. Or I am writing the same thing in a different way. 2 is less than or equal to x plus 1 by x, and which is less than infinity. And this is true for all x is positive. So therefore, this is this infimum and this is the supremum. So therefore, infimum of A6 is 2 and the supremum of A6 is infinity. Supremum does not exist. Is this clear? Hello? Is this
Yes, sir.
explanation clear to you?
Yes, sir.
Yes, sir.
Okay. If it is, then I will move to a similar question of this one. It's almost similar one. You please answer. Again, I'm giving you the hint. Use the same inequality, arithmetic mean and geometric mean inequality. So I'm calling this as A7. So this one. 2 power x plus 2 power 1 by x, and when x is positive. Now you tell me what is the supremum and infimum of this set. Can anyone make a guess? Just make a guess.
Infimum 5/2.
Infimum is? You please think of this question. Huh?
Infimum is 2 root 2.
Hmm.
Supremum
Yes.
is the infinity.
Okay, sir. We will work out, sir. Again, I am using the same inequality. So this one. Just now we have seen x plus 1 by x is always greater than or equal to 2, right? Hello? Yes, sir. No,
Sir.
this is true.
Yes,
For all
sir.
x is positive.
Yes,
Now
sir.
use the arithmetic mean and geometric mean inequality for this one. So 2 power x plus 2 power 1 by x over 2, which is greater than or equal to square root of this one, 2 power x into 2 power 1 by x. So this is square root of 2 power x plus 1 by x. Do you agree? This is obvious, you know.
Yes, sir.
So since x plus 1 by x is greater than or equal to 2, so that implies 2 to the power of x plus 1 by x is greater than or equal to 2. Okay, so therefore this inequality is greater than or equal to this is the inside of the square root is greater than or equal to 2. Now you take the square root of this one. Hello, now you take the square root, then what we get? 2 power x plus 1 by x whole square. Square root is also greater than or equal to root 2. So therefore 2 power x plus 2 power 1 by x by 2 is always greater than or equal to root 2. This means 2 power x plus 2 power 1 by x is greater than or equal to 2 root 2. Hello?
Sir. Yes,
Is
sir.
this clear?
Yes,
Is
sir.
this clear?
Yes, yes, sir. Clear.
Sir. 2
So
power x
there
plus
is
1 by x is greater than or equal to 2 square, sir.
2. Yeah,
Clear.
this is right. This is correct.
Yes, sir.
So this
Yes.
is 4. So here there is a type error. This is 4.
Yes, sir.
So this is square root of 4 is 2. So I can correct this one. So this is twice. And now here we get 2 times this one. So this is 2 times 2, which is 4. Is this okay? Now it is okay. And this is true for all x belongs to, for all x is positive, right? Therefore, so 4 is the infimum and supremum is does not exist. Means this is infinity. Therefore, I'm writing infimum of A7 is 4 and the supremum of A7 which is infinity. Is this okay? Yes.
Okay, sir.
Okay. Okay. Next, we'll move to one more example, and then we'll move back to the properties of infimum and supremum. So meanwhile, in between, if you have any doubts, you can stop me and you can ask or you can raise the questions. Okay. So this one. So I'm taking A8 as another example. This one. So x belongs to R. Collect all the real numbers which satisfies this inequality. Say this is x square plus 2x plus 3, which is less than 0. Now collect all the real numbers where this inequality satisfies. Hello? So this is, you just factorize this quadratic expression as x plus 1. Can we factorize this?
No. No, sir.
What are the roots of this one? I think I have taken a wrong example. I think this we have already discussed in the sense of complex roots, right? What is the discriminant of this quadratic expression? So b square 4 minus 4ac, which is 12 less than 0. It has no real roots. Therefore, a8 is empty set. Hello? A8 is an empty set. So therefore,
Yes, sir. Yes, sir. It is empty set.
we have discussed previously what are the supremum and infimum of an empty set. So now I am
Supremum
moving
of
back to Sam, right? We have already discussed this one, right? So now you
Okay,
collect
sir.
all the real numbers x belongs to R such that this expression is positive. So x plus 6, which is positive. Now can we factorize this expression? Can we factorize? I think we can factorize this as x plus 2 into x plus 3. This is positive. We need to find all the real numbers where these two factors are positive, and this is, we can write geometrically or graphically, which is easy. So look at or locate the roots of this expression. So somewhere here is minus 3 and somewhere here is minus 2. You take any real number beyond the 2, this expression is always positive, or this is positive, not minus. So this is positive. Between minus 3 and 2, it is negative, and then below the minus 3, the expression is positive. Now you collect all the real numbers where this expression is positive is precisely the following. This A9 is same as you take minus infinity to minus 3 union and minus 2 to infinity plus infinity. Now you tell me for this set A9, what is the supremum and what is the infimum?
Minus infinity and plus infinity.
It's obvious, you know. Infimum
Equal
of
minus infinity.
A9 is minus 8 and the supremum of A9 is infinity plus infinity. It's easy. Okay. Now I am moving to properties of this infimum and supremum. That's important. Okay. In residential junior college lecturers, there is a question on this topic, infimum and supremum. We will discuss it after discussing the properties of infimum and supremum. Okay. Properties. First property, which is very trivial one. If S is singleton set, S is a singleton set, then what is infimum and supremum of this set? Or if S is a singleton set, I'll write both the way result. If S is a singleton set, if and only if infimum of S is same as supremum of S. Is this okay? We prove it.
Yes, sir. Okay, sir.
It is obvious. If S is singleton set, then infimum and supremum are same. So therefore, infimum and supremum are equal. If infimum of a set is equals to supremum of a set, then we have to show that S is a singleton set. So I am proving this way. Infimum of S is same as supremum of S. Then we need to show that S is singleton, right? So I'm calling infimum and supremum are equal and equals to A, right? Then we have to show that S is a singleton set A, right? So infimum means A is infimum means A is less than or equal to X. This is true for all X belongs to S, right? This is the definition of infimum, and infimum is an lower bound. Therefore, all the elements of S are left of A. And now I'm using the definition of supremum. If A is supremum, means A is an upper bound. Therefore, all the elements of A are left of A, and this is true for all X belongs to S. So combining these two, so we have A is less than or equal to X is less than or equal to A for all X belongs to S, and we have only one possibility, X is A. Therefore, you take any X in S and it becomes A, therefore S is singleton. Is this okay? So this implies S is precisely a singleton set A. Singleton means set containing with only one element is known as singleton set. Right? So this is the first property. If the set is a singleton set, then its supremum and infimum are same. Or if infimum and supremum are same, then the set is a singleton set. Then the next property. So property number 2. So this is obvious. Infimum of a set is always less than or equal to supremum of AS. If I write this, then it contradicts with the empty set. So therefore here S should not be an empty set, right? So this is obvious.
Yes, sir.
This is obvious, provided S is a non-empty set. Okay, and this is trivial, so I am not going to prove this statement. Now look at the another statement, which is very interesting one. We can prove it easily. Let S is non-empty and subset of R. S is a non-empty subset of R and bounded above. And bounded above. Okay. Define a new set. I am defining new set as this one. And you call this as A belongs to R, and define a set A plus S. So I am defining what is the meaning of A plus S is this. So this is A plus X such that X is belongs to the set S. Means add A to every element of S. Right? Then we have the following properties. If S is bounded above, then A plus S is also bounded above. Right? So then the properties are the following. First one, infimum of small A plus S. So this is A plus infimum of S. There is no change in the result. You just add A to the infimum of S. And similarly, you can guess one more result about the supremum. Supremum of A plus S, you just add A to the supremum of S. So this is A plus supremum of S. Right? One can ask with curiosity, what happens if infimum of A minus 1 if we define similarly? Then can we get the same result? Infimum of A minus S is same as A minus infimum of S? No, that is not true. Later we see it. Is my question clear to you? Hello?
Sir, yes, sir. Yes,
Yes,
sir.
sir.
What I'm asking is, you may be curious to know that this one, right? Infimum of A minus S. Can this is A times or A minus infimum of S? So this is suddenly no. Okay. And the fourth result, and it is also a trivial result, fourth one, you take any non-empty subsets of A and B. Here both A and B are non-empty subsets of R, such that A is less than or equals to B. Oh, we cannot write this way, right? The way of writing is not correct. So I will write in another way. Such that small a is less than or equal to small b for all a belongs to A and for all b belongs to B. Then the conclusion is this one. Then can you guess what's the result? Then supremum of A is always less than or equal to infimum of B. This one. Okay, and I'll prove it. It is a simple result, so therefore we can prove it. It's not so difficult to prove. Okay, and in a competitive examinations, I believe that proofs are not required or not necessarily. If we know the result, then we can apply. But this is very simple one, so I am writing. So what is given as A is less than or equals to B for all A belongs to A, right? So this means B is an upper bound of A. Do you agree? Now look at the definition of an upper bound. If all the elements of A are left of some real number here, so left of B, so all the elements of A are left of B, therefore B is an upper bound. So therefore supremum of, so clearly here this B is an upper bound of A, so therefore supremum of A is less than or equals to B. The supremum is the least upper bound of A. So therefore supremum A is less than or equal to B. And again use the same inequality. So supremum of A is less than or equal to B. This is true for all B belongs to B. Therefore this supremum is the infimum of the set B. So therefore we write supremum of A is less than or equals to infimum of B, and it's trivial. Is this clear? Hello?
Yes, sir.
Yes, sir.
Yes, it is obvious. Here, this B, this is true for all B belongs to B. Therefore, all the elements of B are right of supremum of A. Therefore, that will be the infimum of B. So therefore, supremum of A is always less than or equal to infimum of B. So the fourth result. And the fifth one. So, and this is obvious, I believe that. So infimum of minus S is same as minus supremum of S. Okay, and one more. You can guess what is the similar result. Supremum of minus S, this is equals to minus infimum of S. So therefore, now you can update your previous question is the following. What is infimum of A minus S? This is A plus, you can write infimum of minus S. Now infimum of minus S is A minus supremum of S. So this is the answer for the previous question. Okay, and proofs for this set, these two results are easy. If you need the proof, I can explain, or I will explain. It's 1 or 2 lines so that I can explain. Now you let, I am calling supremum of S as say small a or U. Then if U is the supremum of S, then what happens? Supremum is an upper bound. Therefore, all the elements of S are left of some real number, and that real number is U here. And this is true for all S belongs to S. Now you multiply with minus sign, then we get the inequality reversed. So this is true for all X belongs to S. And what is minus S? Minus S is you take the negative of X and X is in S, right? So this is precisely minus U. Now here you see this minus U is the infimum of this set minus S. So minus U is the infimum of S, right? So therefore minus U equals to infimum of S. And what is U? U is the supremum, right? Infimum of minus S, not S. Infimum of minus S. So this implies infimum of minus S is minus of U. But what is U? U is supremum of S. Okay. So similarly, you can prove the second one, supremum of minus S as minus of infimum of S. So with this two results, I will write four similar result to this one as follows. This is the question asked in the uh, residential junior college lecturers exam, right? So if K is positive, if K, I'm using K, you can call as C or S or any variable you can use. If K is positive, then infimum of K into S is same as K times of infimum of S, and supremum of Ks is same as K times supremum of S, right? If K is negative, if K is negative, then infimum of Ks is not minus K times supremum of S, and supremum of Ks when K is negative. So this is K times infimum of S. One can prove this easily. Agree? Hello? Are you following this statement?
Yes, sir. Yes, sir.
Say one times you say yes, yes, then I can say that or assume that you are following my, okay? I believe that, huh? So meanwhile, or in between, you say yes, sir, we are following, or yes, we are understanding what you are saying. Okay. Now I am writing another property of this one, infimum and supremum, and after that I will discuss remaining problems. Okay. So another property of infimum and supremum is the following. So supremum is a linear function. What is the meaning of linear function means? What is linear transformation? What is when we say a transformation in linear, T of alpha plus beta is same as T of alpha plus T of beta, right? So similar result is there here. Supremum of two sets, say A plus B, is same as supremum of A plus supremum of B. So this is known as the linearity. Supremum of A plus supremum of B. And infimum is also linear. Infimum of A plus B is also infimum of A plus infimum of B, right? Now you answer the remaining two questions. What is the supremum of A minus B? This is supremum is linear, right? So we write supremum of A plus supremum of minus B, and supremum of minus B is same as supremum of A minus infimum of B. This is, and infimum of A minus B Infimum is linear, so therefore we write infimum of A plus infimum of minus B. And in what is infimum of minus B? So infimum of A minus supremum of B.
Yes.
Is this clear? Hello? Yes. Okay, okay. Now I will move to few examples on supremum and infimum with the help of linearity of supremum and the negativity of the supremum and infimum. So examples. Example. This time I'm calling this. If for the following sets, find infimum and supremum. So this is the question. The first question is this one. 1 minus 1 by n such that n is belongs to n. So there are two ways to find the infimum and supremum of this set. Okay. So there are two ways. Simplest way is this one. Since 0 is less than 1 by n is less than or equal to 1 for all n belongs to n, right? This is true. So therefore you multiply with a negative sign. So minus 1 is less than or equal to minus 1 by n, and which is less than 0 for all n belongs to n. Do you agree? So now adding 1 both sides. So this becomes 0 is less than 1 minus 1 by n is less than 1. So this is true for all n belongs to n. So therefore, infimum of the set, you call this as say A1 or A10. So this is infimum of A10 is 0 and supremum of A10 is how much? Which is 1. Is this clear? Hello?
Yes, sir.
Yes, sir.
Okay.
Sir.
Okay. Okay. So similar question, but this similar question. So I'm calling this set as A11. 1 by m minus 1 by m such that both n comma m belongs to n. This one. Find infimum and supremum of this set. So first I will find infimum and supremum of this set. 0 is less than 1 by n is less than or equal to 1 for all n belongs to n, right? Do you agree?
Yes.
So this implies infimum is 0, infimum is 0 and supremum is 1, right?
Infimum is 0.
Now you
Supremum
take
is
another part, minus 1 is always less than or equal to 1 by m is less than 0 for all m belongs to n, right?
Right.
So for this set,
Minus 1.
infimum is minus 1 and the supremum is 0. Agree? Hello?
Yes, sir.
Sir, yes.
Okay.
Sir,
Now
yes,
we
sir.
use the linearity of supremum and the linearity of infimum. Therefore, infimum of, you call this as A set and you call this as B set. Now my A11 is same as A plus B. Agree? A11 is A plus B.
Yes, sir.
Therefore, supremum of A11 is supremum of A plus infimum of, no, not infimum, it's also supremum. This is supremum of B, right? What is supremum of A? Which is 1 and supremum of B is 0. Therefore, supremum of A11 is 1. Supremum of this set is 1, supremum is 1. And similarly, infimum of A11 is same as infimum of A plus infimum of B. Right? So this is infimum of A 0 and infimum of B, which is minus 1. So therefore it is minus 1. So for this A11, supremum is 1 and infimum is minus 1. Are you following?
Sir, yes, sir.
yes.
Follow.
Okay. One more problem of the same kind. You please answer. So, problem of the same kind. You tell me what is the infimum and supremum of A12 set. So this is A12 equals to 1 by 2 power n plus 1 by 3 power n such that n is a natural number. Now we find what is the infimum and supremum of this set. Can anyone make some guesses? So again, use the same trick of the previous question. You call A as
5 by 6.
exactly 0 and 5 by 6. There are two ways. I'm not saying two ways. There may be another ways, but uh, so there are two ways to calculate the infimum and supremum. You call A as 1 by 2 power n such that n is in n. So what is the supremum and infimum of this set? Infimum is 0 and
Supremum
supremum is
1 by 2.
1 by 2 exactly. And you call another set as B, so which is 1 over 3 power n such that n is in n. So what is the infimum of this one? Infimum is 0 and supremum is 1 over 3. Agree? Now use the linearity of supremum and infimum. So therefore supremum of A12 is supremum of A plus supremum of B, which is 1 by 2 plus 1 by 3, which is 5 by 6. And infimum of A12 is, so infimum of A plus infimum of B, which is 0. Is this okay? Hello?
Yes, sir. Yes.
Okay, fine. And one more problem of the same kind, almost same, but I am replacing the sign in between uh, the two. So this is 1 over 2 power n minus 1 over 3 power n. So if I take this one, and n is allowed to be a natural number. What is this? Tell me the supremum and infimum of this set. You can do it, or you can work out. Nothing
0,
difficult.
1 by 6.
0 and 1 by 6. Right. So you take this as a exercise. Very simple one. And I'm writing one more example. A4. So I'm calculating the ratio of m and n such that both m and n are natural numbers and satisfies this relation. M is less than 2n. Now you tell me what is the infimum and supremum of F14. A15 you take it as a homework. You can practice this one. 2 power p minus 1 by 2 3 power s p or q plus 1 by 5 power s such that p comma q comma s are natural numbers. So you take this practice problem. Now can you tell me what is the answer for this one? So this
0,
A14 0
0 and 2.
0 and 2.
Infimum 0, supremum 2.
Yes. When n is large number, then m by n is 0. And when m is equals to n, then it is 1 by 2, or write 0 is less than, from this I am taking, natural number is always greater than 0, m is less than 2n. So take the division with n, so this 0 is less than m by n is less than 2. So therefore infimum is 0 and supremum is 2. So A14 is precisely lies between 0 and 2. So infimum is 0 and supremum is 2. Okay. And one more example. So you tell me what is the infimum and supremum of this set. M and n are allowed to be the natural numbers. So m by n plus 4n over m, such that both m and n are natural numbers. Can you tell me what is this one? Infimum and supremum? Yes, please. What is the infimum and what is the supremum? So the hint is use arithmetic mean is always greater than or equal to geometric mean. You can use it. Hello?
Sir,
Therefore,
yes, sir.
m by n plus 4n by m over 2 is always greater than or equal to square root of m by n times 4n by m, and which is 2. So therefore A16 is always greater than or equal to 4, and which is this one. So therefore infimum of A16 is 4
4.
and supremum is
Infinity.
does not exist, which is in. It is okay.
Yes.
Yes, sir. Yes.
Okay. Okay. One more, but it is quite interesting and simplest one also. You please tell me what is the infimum and supremum of the following set. You tell me what is the infimum and supremum of this set. So if I am writing A17, so this is very simplest example, 0.2, 0.22, 0.222. I'll write one more, 0.222, and so on. Can you tell me what is the infimum and supremum of this set?
0.
Yes, please.
0.2, sir.
0.2.
0.2, 0.22, 0.2222, and so on. There is no special about 2. You can replace with any number you want. You can replace 2 by numbers between 0 and 9. Then we can talk about their infimum and supremum.
Infimum is infinity, supremum is 0.2.
Supremum is 0.2. Okay. So clearly look at, is 0.2 less than 0.22? Yes. 0.22 is always less than 0.222. So therefore this is an increasing sequence. If it is an increasing sequence of number, the first number itself is the infimum. So therefore infimum of A17 is 0.2 only. Is this okay? Infimum of A17 is 0.2. Is this clear? Because each term are in increasing order. So 0.2 is less than 0.22 and so on. Now what is the last number in this set? The last number is 0.22222 and so on. And what is this number? This number is same as 2 over 10 plus 2 over 10 square plus 2 over 10 cube plus and so on. So therefore, or we can talk about this in terms of the sequences. This is an sequence given by this one. 2 over 10 power n, and n is from 1 to infinity, right? And this sequence is increasing and bounded sequence, therefore it is convergent, and we find the limit of this sequence as follows. So this is a infinite geometric series. So 1 plus 1 over 10 plus 1 over 10 square plus and so on. So this is an infinite geometric series. So therefore we have the sum is 2 over 10 times a by 1 minus r is 1 over 10 here. Agree? So this is 2 over 9, I think. So therefore this therefore the last term of this A17 is 2 over 19, and which is the supremum of A. Is this okay? So therefore supremum of A17 is 2 over 9. Is this okay? Hello? Infimum is 0.2
Okay.
and
Okay, sir.
supremum is 2 over 9. With the same logic, you can replace 2 by 3, 4, 5, 6, 7, and 9, and you can work out yourself. Okay. So I have the last example of I've discussed, and this is based on the greatest integer function and fractional part of x. I don't know whether I think all you know what is an greatest integer function and these things. Now you see this one. Find the infimum and supremum of the following set. So square root of n minus bracket n. So this is square root of n such that n is in n. N is in n. Right? Or you can write n square also. I can come back to this one later. And now what is the infimum and supremum of this set?
0, sir. 0, 0. Singleton set 0.
This is precisely the singleton set 0. Because, so this is related to fractional part of x. Fractional part of x. So this is defined by this symbol. Fractional part of x is x minus step x. And this is always x minus step x is bounded by 0 and 1. The range of this sequence, range of the fractional part of x is 0 and 1. If x is an integer, then fractional part of x is 0 for all x belongs to x. So therefore here n square, we are taking square root, therefore this is an integer, minus fractional part of integer is always 0, singleton set 0. Therefore infimum and supremum of this set is?
Both are 0.
Both are zeros, exactly. So infimum of A18 is same as supremum of A18, and which is 0. They are equal, therefore the set is a singleton set, and which is equal to the 0 set. Okay. So with this I will stop, or else I will go for the next topic. Okay. So I will stop it here, and tomorrow we will discuss the Archimedean property and the sequences of real numbers. So there are other properties of sets known as open sets, closed sets, and derived sets, and that will be covered in the topic of metric spaces.